So, welcome back. So, we are into the third week. As I mentioned in my earlier class, that from this section, we will be talking about this is the basic of the mass sensitivity of QCM. Now, when we talk about the mass sensitivity, now let's see how the frequency change is happening. So, this is on the y axis, you have the frequency change, and this is the basic crystal sitting out there. Now, you have some molecules which are added. The very moment the molecules are added, automatically, as I said you, if this is moving at a certain frequency, once you add this, the frequency is going to come down. As you could see, it's come down. And if you add more molecules, 3, now here you see almost 6 molecules. So, in other words, adding a few more of these on it, it is going to go down even further. You realize that's exactly what you are seeing, how this curve is coming down. So, this is how. So, say for example, now if you remove some of them practically, then this is now going to go up. You remove more of those, is going to go further up. Okay. So, you see in a real life, you can actually see the addition and subtraction of the mass which is happening. So, a quartz crystal oscillator at a constant frequency when an appropriate voltage is applied. So, you are applying a voltage and maintaining a constant frequency. The oscillation frequency starts to decrease as molecules begin to deposit on the crystal surface. Okay. And the frequency further decreases as more and molecules get deposited. Now, if you replace these molecules with, say, antibodies, DNA, proteins, toxins, of anthrax. This is one approach where they have a very sensitive balance which has the ability to detect the changes which are happening in the frequency domain. So, two things to remember: change in frequency, delta f and delta m. And if you have an expression for this, what Sauerbrey equation offers you, delta m, which is change in mass, is equal to constant c, which is, okay, when we talk about the constant c, so this constant c comes from some of these parameters: the density of the quartz, total added mass, velocity, thickness of the quartz crystal, and all those things. Okay, from where, and the detailed equation is pretty interesting. So, minus c 1 upon n, I told you, look for the overtone number, and delta f. So, by changing the voltage, you can maintain it at a certain frequency, and if you keep the voltage constant, it will continue to vibrate at that unique frequency. But if you add a mass on it, that mass change will alter the frequency. So, if you look at the equation, it is almost like there is a straightforward linear relationship between change in frequency and change in mass. So, if you see here, as the mass is increasing, frequency is decreasing. It is a very, very linear relationship, but there is a catch where this linear relationship holds. And the catch is here. When I was showing you the first slide, I told you I will come back to this slide, is out here. There are a few small lines which are written here, and I did not discuss this. So, change in added mass m on the crystal can be treated as an equivalent of the crystal itself, provided that the added mass is, now 3 conditions important: small compared to the crystal mass, like you cannot add something which is more than the crystal mass, you understand. So, if the crystal mass is 1 unit, what you are adding must be far less than 1 unit. Point 1. Rigidly adsorbed with no slip or deformation imposed by the oscillating surface. That means when something is getting there, it should rigidly adsorb on the surface. It should get entrapped into the surface. If it is not, if it is behaving like a viscoelastic material, or if it is kind of slipping out of the surface, it's rolling on the surface, it's moving like this, it's not going to work. So when I am adding something like this, it should remain like this. It should not be like, it's slipping away, or it's moving like this, and all those kind of things won't work. So quartz crystal microbalance, you have to be extremely careful. Standard quartz crystal microbalance won't work under those situations. And evenly distributed over the surface. Why it is evenly distributed over the surface? Because of this situation, if you look at it. If it is not evenly distributed, what will happen? Say for example, your film is like this. Say for example, this is your crystal surface and your film is like this. The shaded part is the film. So you will see some different kind of frequency at this zone and a different kind of frequency at this zone and different kind of frequency at this zone, and this whole thing is going to go completely in a different tangent. So first of all, it should adsorb firmly on the surface. Point 1, it should not slip on the surface. And second thing, it should be uniformly distributed on the surface. If we maintain that, then quartz crystal microbalance is a really powerful tool to measure the changes. Now, how the instrumentation really looks like. So here you have the quartz crystal, you have the crystal holder sitting out here. Now here is the oscillator, which generates a frequency counter, at what frequency things are happening, and this is attached to the personal computer. This is a very simple and actually it's extremely simplistic way of showing it, but essentially it's out here. This is the basic thing. Now having said this, think of a slightly different situation. We are talking about quartz crystal microbalance, so we are assuming everything should stick properly, adsorb properly. But so when we talk about adsorption, we see these kind of adsorptions with gas molecules or in dry conditions, things which adhere on the surface. But when you talk about the molecules like what we have been dealing, these kind of molecules, these are not molecules, or these are not things which remain very dry. They always work better in the presence of water. And if the water enters into the system, then it's a very different ballgame. So say for example, when I'm showing this is in the air. So say for example, this is inside the water, or there is a thin film of water, then how it is going to behave? How all these frequencies are going to change? Are you realizing the problem? Because when we talk about the biosensing, we are talking about molecules which does best in the presence of water molecules. So for such things will QCM work. Okay. So coming back, the limitations. When you talk about the limitations of QCM and the failure of Sauerbrey equation, for the Sauerbrey equation to hold, the layer of the sensor must be thin and rigid. Interestingly, rigidity is not the way biological molecules work, and firmly attached to the crystal surface. if these conditions are fulfilled, Sauerbrey equation could be used to calculate the mass of the added layer. However, if the sensor layer is soft, which is exactly the biological molecule, thick, or not coupled to the sensor surface, so it's kind of there are slips, the Sauerbrey equation is not valid. The model will fail in these situations and the calculated mass will be underestimated. So, you realize for standard Sauerbrey equation to work, there are some prerequisites. So, that is why for a long period of time Sauerbrey equation has been used, the QCM has been used for gas sensing. So, where what you do, you pass the gas through a chamber where you get rid of the water and everything. So, you dry up the gas and you put it on the microbalance and measure it. It is a fantastic sensor for that kind of situation, but not for this kind of situation. Okay. So, that brings us to a next level. What happens in wet conditions? The real biological scenario. The real life situation for biosensors, quartz crystal microbalance with dissipation, which is called as QCM-D, where D stands for the dissipation. So, first of all, let us try to imagine the situation. So, say for example, this is something which vibrates like this, okay, in air. Now, think of it, this is all happening in the air. Now, if I take it inside the water, will it vibrate like that? By your common sense, you can take it won't vibrate like that because there are film of water which is going to prevent its movement. Now, if you look at the slide, in the liquid environment, however, molecular adsorption includes contribution from associated liquid molecules as an additional dynamic mass via direct hydration, solvation and entrapment within the adsorbed film. Adsorption can produce soft viscoelastic film. So, to imagine it something like that. Say for example, this is the crystal and you have water molecules, you have your analyte sitting in them. So, there are this material is now the situation is more like a viscoelastic film. It is kind of like this. Film is slipping on the surface, okay, and the resulting layer may not fully couple to the oscillating crystal. So, if you remember the conditions which were laid for Sauerbrey equation to work. So, it should be rigidly coupled on the surface, there should not be any slip and the mass of course has to be very low as compared to the mass of the crystal. But here you see it is not fully coupled. This can lead to the dampening or energy loss of the oscillation, because such situations, say for example, something which is kind of oscillating like this, you put a lot of water into this, you will see the oscillation frequency is going to go down because it becomes heavier. So, if you use a sensor which is already now imbibed with water or has absorbed a lot of water, then you have to alter the equation, because then your baseline has changed, the frequency, the baseline frequency has completely changed and your basic theory is not going to work here, that delta m is linearly related to delta f, where delta m is your change in mass and delta f is your change in frequency, because in this situation your frequency is working in a very different way. There is a dissipation because of the it is absorbing. So, in a real life what is happening, say for example, this is a dry crystal and I put a say phosphate buffer saline containing antibodies on top of it. Now, these water molecule will get adsorbed on this surface. So, it will show a different kind of dampening onto it. So, the frequency change also will include a dampening process. Coming back to the slide, this can lead to the dampening of or energy loss of the oscillation. This is what I was trying to tell you. There will be a loss of energy in the oscillation process of it. The mass of such film cannot be determined accurately by measuring the frequency change alone. Both frequency change delta F and energy loss, that is measured as dissipation energy. So, delta F, now another new term is coming into the game, delta D or delta D, whichever you want to denote it, which is the dissipation changes need to be measured to determine the mass change of a viscoelastic film. So, now delta M or change in mass is related to delta F and delta D, which is the change in frequency, and this is dissipation changes. Furthermore, by monitoring both delta F and delta D, additional structural information, conformational change in the film, cross-linking, swelling can be obtained, because now you are monitoring another parameter, which is the dampening parameter, and we will come to that, how the dampening parameter works in this situation. Now, when we talk about QCM-D and its utility in biosensing, QCM-D also provides real-time information on the viscoelastic property. Most of our biological molecules, what we see, are viscoelastic in nature. Most of these polymers are viscoelastic in nature of the adsorbed film, such as viscosity, elasticity, and density. Now, you are dealing with three different parameters. Viscosity is resistance to the flow or the friction which it offered during the flow. Elasticity, all of you know, and density is mass per unit volume. Okay. The maximum mass sensitivity of the technique in liquid is less than 1 nanogram per centimeter square, which is a unique thing. 1 nanogram per centimeter square is no easy feat. The maximum film thickness that can be measured varies from several to 100 nanometer to a few micron, depending on the rigidity of the film. QCM-D has wide range of application in various fields of science. Some examples include molecular interaction, that is protein-protein interaction, molecule to surface interaction, the affinity of the biomolecules to the binding site of the functionalized surface, the buildup of polymer films and their interaction with different constituent of liquid medium, and the effect of surfactants on various coatings, biosensor application, etc. So, if you look at the utility of QCM-D, it is extremely robust. Only point is that you will have one more parameter with along with delta change in frequency will be delta D. You have to have the dissipation parameter to be taken into account, and then you can actually change the change in mass. Not only that, say for example, a protein in the initial phase is like this, then it becomes like this. This change also can be monitored, how the conformational geometry of the protein changes depending on the situation, adherence, and over a period of time. So, you could have a real-time monitoring using QCM-D, and that is the beauty of this technique of QCM-D, that you can monitor multiple things. And again, to reiterate, protein-protein interaction. So, for example, you have one set of protein and there is another set of protein, how they are interacting, you can monitor it. Molecule to surface interaction. So, you can coat the surface with certain things, whether it is a hydrophobic surface or a hydrophilic surface based on its viscoelastic nature, because you are taking into account the viscosity, mind it, elasticity and density. You can see the change. How much is the interaction happening? What kind of interaction is happening? Buildup of the polymer films, how the film is forming. Does it forming a continuous film? Say for example, in polymer, sometimes polymer forms a continuous film, self-assembled monolayers. Sometimes it forms broken up films. You can actually monitor such unique I would say, molecular events which otherwise is not feasible with any other form of sensors. Okay. So, apart from it, you can also understand how different kind of liquid medium could change the conformational geometry and movement, self-assembly of the different molecules. Okay. Now, QCM-D is a deviation from the classic Sauerbrey equation. Okay. The linear relationship between frequency and mass as defined by the Sauerbrey fails for viscoelastic film. Hence, it is important to take dissipation into account when quantifying viscoelastic mass. Remember this word, viscoelastic mass. Okay. Dissipation is defined as the inverse of crystal's quality factor Q as expressed by D is equal to 1 upon Q, where E dissipation upon 2 pi E, which is the stored, where E dissipation is the energy dissipated in one cycle and E stored is the energy stored in the oscillating system. Okay. Followed this, there are two ways you can define this QCM-D. It could be defined either by equivalent circuit model or it could be defined by the mechanical model. If you define it by the mechanical model, this is where the mass we are seeing. Okay. So, when you are defining it based on these two models, when a piezoelectric quartz crystal resonates, both electrical current and the mass oscillate simultaneously. Okay. Therefore, quartz can be represented by either its equivalent electrical circuit as shown in the figure or a mechanical circuit shown out here. Okay. The electrical circuit model consists of an inductance, Henry, capacitance, resistance in series, these are all connected in series, and a parallel shunt resistance CO. The mechanical circuit model consists of mass M, as I was showing you, connected to a spring with a spring constant of K, this is that spring with a constant K, and a dashpot with a dampening of Y. The two models can be compared as follows. L1 represent the oscillating mass, C1 represent its elasticity, and R1 represent the energy loss in the system, and C0 is the shunt capacitance due to the overlap of the electrode on the crystal surface. C0 is purely electrical and does not have any represent in the mechanical world. So, this particular thing, this component, this is purely electrical thing. There is no equivalent mechanical counterpart into the system. And if you look at energy dissipation in electrical circuit model can be defined as I mentioned, D is equal to 1 upon Q, where R1 upon 2 pi multiplied by frequency, by where F refers to the frequency. The two most common approaches that use electrical circuit model for measuring energy dissipation are resistance analysis or impedance analysis. There are two ways you can do, and mostly there is a third technique which is being used most currently. So, if you look at the resistance analysis, in resistance analysis what you do in QCMR, the resistance of the crystal can be measured by introducing a small resistor into the circuit and measuring the voltage change. So, you introduce a small resistance or resistor into the circuit and you measure the change in voltage. If the shunt capacitance C0 has been cancelled and measured current of the resonating crystal's equivalent circuit will be proportional to the crystal's resistance R1, which is the sum of the losses. This approach, however, does not provide an absolute value because L1 is not known. So, if you look at L1 here, that is what I was trying to tell you, this value is not known. So, L1 is not known in this type of measurements. Also, the true cancellation of C0 may not be achieved if the crystal is significantly loaded. For these reasons, the resistance approach provides relative structural data. You do not get a very unique absolute data in this, but when you talk about the impedance analysis, it is slightly different. In the impedance analysis, QCM-Z, which is represented by, is a more defined approach for measuring energy loss. In this method, all 4 elements of the crystal equivalent circuit can be determined by impedance analysis. So, how you do so, it's very interesting. Here is the equivalent circuit. Okay. Now, in order to, so you have to determine all the 4 elements like L1, C, R and the shunt resistance. Okay. The setup includes a frequency generator that provides varying input frequencies to the equivalent circuit. The current and phase are recorded at each frequency of the frequency sweep, allowing all the 4 components L1, C1, R1 and the shunt to be numerically fitted. The limitations of this approach is that fitting of this equivalent circuit works only when crystal is at a steady state. The crystal needs to be stabilized at each frequency step interface, and that is why the data generation is extremely time consuming in this effort. It takes a hell amount of time to use impedance analysis QCM-Z process for data analysis, and that is why each one of this process comes with its set of drawbacks. And I told you that there is a 4th method which is most commonly or getting extremely popularized nowadays is this one, which is quartz crystal microbalance with energy dissipation. A 3rd approach that is gaining increasing popularity is QCM-D. In this method, the quartz crystal is excited to a resonant frequency for a short period by applying a driving voltage. So, here you have the crystal, you have the electrode, and you basically it is excited with a resonant frequency for a short period by applying a voltage across it. So, you are applying a voltage across it and it is resonating. The driving voltage is then turned off and the voltage decay over the crystal is recorded as a function of time. Now, the voltage over the crystal decay as exponentially dampened sinusoidally given by this particular expression, where W here A is the amplitude, here is the decay time constant, F is the frequency, here is the phase angle, and the decay time constant is related to the dissipated factor by this relationship. So, this is currently the most widely used QCM-D method. Therefore, by numerically fitting the decay curve, both frequency and the dissipation of the crystal can be obtained simultaneously. The decay time constant depends on the rigidity or softness of the mass adsorbed on the crystal surface. For example, rigid materials such as metal films coupled with the oscillating quartz, when the driving voltage is turned off, the oscillation takes longer to decay. In other words, the decay curve will be longer. On the other hand, if the adsorbed mass is soft or viscoelastic such as protein, lipids, etc., its coupling with the oscillating quartz is poor. The flexible viscoelastic mass dampens the crystal oscillation, causing decay faster, and the decay curve will be shorter. I will show you a schematics that will help you to understand it. Here it is. You look at the decay curve. Now, they settle down. You are about to introduce this. They haven't still gone to the surface, the decay curve. But now, when we talk about things which are viscoelastic material, as I was mentioning here, look at it. For example, rigid material like metal films couple well on the oscillating quartz, because how we did it, you, as it is being mentioned, in the 3rd approach gaining increasing popularity of is QCM-D. In this method, the quartz crystal is excited to a resonant frequency. Fine. It is. So, now if you look at this picture, so it is moving at a resonance frequency, it is already there. Now, what you wanted to see the change of this resonance frequency, how it is coming down, right. So, let us see what it says, right. In this method, the quartz crystal is excited to a resonant frequency for a short period by applying a driving voltage, right. Once again, I will go here. So, you apply a driving voltage across this and this is resonating. Now, okay, the driving voltage is then turned off, then you switch off the voltage. So, it is resonating like this. and then you switched off the voltage. So, it will continue to resonate for a while, right. And the voltage decay over the crystal is recorded as a function of time. So, you know after how much time it is going to decay and how it is going to decay. The voltage over the crystal decay has exponentially dampened the sinusoidal wave given by. Then I talked about all the expressions which are present there. Now, when we talk about this part, numerically fitting the decay curve, both frequency and dissipation of the crystals can be obtained simultaneously. The decay time constant, remember this, the decay time constant depends on the rigidity or softness of the mass adsorbed on the crystal surface. Whether it is rigid or it is soft will determine the decay time. For example, rigid material like metal films couple well, again there is a word, couple well with the oscillating quartz, and when the driving voltage is turned off, the oscillation takes longer to decay. In other words, the decay curve will be longer. On the other hand, if the adsorbed mass is soft or viscoelastic such as proteins, lipids, etc., its coupling with the oscillating quartz is poor. The flexible viscoelastic materials dampen on the crystal oscillation, causing it to decay faster. Now, if you look at this structure, it will help you to understand it. So, this is the first situation I told you before adding. Once they add, it dampens. But here look at it. The point of contact, they are not properly contacted. So, the surface contact of these things are very less. As versus here, there is a better surface contact. When the surface contact is more, the dampening does not happen so fast. When the surface contact is less, they are slipping on the surface, they are moving on the surface, the dampening happens faster. So, this is a schematic representation of the principle of QCM-D. The oscillation frequency decreases as the mass adsorbed on the surface. The rigid mass couple well with the crystal, leading to a long decay curve. The viscoelastic mass couple poorly with the crystal, leading to a short decay curve. Now, these are the most basic fundamental of understanding how QCM-D works. Thank you.